here we are at the AutoFab lab, and we are undergoing the Output Devices Week of the Fab Academy. And one of the assignments is to measure current of one of the output devices that you choose to use for your project. So we are going to look into several ways how to do that. So you see there's all kinds of electronics equipment, measurement equipment, but the ones that we are going to focus on today are this DC power supply, or the so-called benchtop power supply, or you can find that on the internet by the name laboratory power supply or programmable power supply. So we're going to use this in order to provide specific voltage and specific current to a device of our choice. And the second device that we are going to use is this multimeter. And we're going to use this in order to validate the measurements that we get with the benchtop power supply. We are going to use two output devices. One is this DC motor, so if you look at the label, so it says that it's DC motor, 12 volts with 50 RPM, plus minus 12% precision. And then it actually has a gear ratio, so 1/90, so which means that the actual DC motor spins faster. So there's a DC motor inside and there's a gear system, which makes it spin slower, but it has 90 times more torque than the actual DC motor inside there. And the other device that we're going to use is this LED strip. So it's like it was lying around, so it seems to be 12 volts. I think I turned it on once, and we're going to measure how much current it is pulling. So let's focus on the power supply, on the benchtop power supply. So it has two little screens over here and then some knobs over there, so limited amount of those. And then a power button over here and connections for the test, or not the test, but for the probes or for the cables that we can use in order to connect it to our devices. So the red one, so it's always smart to connect to the positive terminal. So here we have the red one connected to the positive one, the black one connected to the negative terminal. And these test clips, they have so these really nice connectors. So we have grabbing connectors. So when you push this button over here, then it's opening up the little grabbing element, and then when you release it, it grabs it. So it's very good to grab a cable. So if you have a cable open end like this, then you can grab it by using these really easily, and it sticks to it. So it's a very reliable way of connecting elements quickly for measurement purposes. So what happens when we are powering it up? So we press the power button and we see that on the left side, which is the current side, so current is measured in amperes, there's 0, and on the right side there's the voltage side, and currently we have 12.2 volts. So with these knobs, so you see under each of those there are some letters. So on the right, under the right one there's coarse, and under the left one there's fine. So, and you use the coarse one to do coarse adjustments, so you can tune the voltage to higher and lower values, but really in big steps. But the idea is that you get to an approximate position with the coarse with a coarse knob, and then you do fine adjustments with the fine knob. So I'm going to adjust it exactly to 12 volts. At least I'm going to try. So like this. Then currently we see nothing on the current indicator because nothing is connected. So once we connect something, it's also going to show us how many amperes the device is pulling. And we can set a limit to the amount of amperes this power supply is able to supply. But in order to do that, we first need to switch the device off. And then we take these test LEDs and we connect them together, we short them together. In a normal situation with a battery, you wouldn't do that, but in order to adjust the limit, the current limit that the laboratory power supply can supply, so you have to do this. And then you turn the power on, and you see that the voltage drops to 0, but the current, it jumps up to 2. And the same concept with the knobs applies here. So the right knob is doing coarse adjustments, and the left one does fine adjustments. So if you know that your device has a limit of current that it can support, and you don't want to kill it, then this is the way how you can set that limit. So you see now I'm going up. So 2 amperes is quite a lot. So I'm going to just tune it down to, let's say, 1.9, and then I'm going to use the fine adjustment knob in order to tune it exactly to 1.9. So now the maximum limit of a current of amperes is 1.9 amps. And so let's disconnect this. And let's see how much current the DC motor is pulling individually. I'm also going to take some notes. So DC motor, how much current it is pulling. So I'm going to connect this, the positive, so the red test LED to the positive cable connector of the motor, and then the black one to the negative one. Arrange everything so that it's relatively manageable by a human being. So also make sure that these connections are not too close to each other. So we don't want, in this case here, we don't want to short the circuit. So we want the positive go to the motor and the negative separately. So now what are we going to do? We're going to switch on the power supply. And let's take a look at the motor. It spins. And let's take a look back on the power supply. And we see that the voltage is 12 volts as we expected, and that the current measurement on the left side is 0.03 amps. So let's write this down. So this is a measurement of the power supply. So it's 0.03 amps. Let's switch the power supply off, and let's introduce the next way of measuring current, which is by using the multimeter. So we used it to measure voltage, and we used it in order to detect short circuits, for continuity testing. And in that case, the test LEDs were connected. So the black is always connected to COM, and then the red one is always application specific. So in order to measure voltage, you can see also on the labels over here. So in order to measure voltage and resistance and the direction of the current and capacitance, you use this connector. But then in order to measure amperes, you need to use one of those. So if you're looking for really small currents, then you would choose these microampere and milliampere jack. But we are measuring a bit larger units, and thus we are going to choose the ampere measurement jack over here. And I've chosen to attach the same kind of test clips over here. And for measuring current with the multimeter, it is important to connect the multimeter in between the power supply and the actual device that we are driving. So we're going to do a trick here. So I'm going to disconnect the motor. Oh, sorry. Disconnect the motor from the power supply test LEDs. And what I'm going to do, I'm going to connect the negative or the black test LED to the ground of the motor. And oops, it fell down. So I'm going to rest it like this. And now here's the trick. So I'm going to take the positive connector, positive test LED of the power supply, and connect it with the positive test LED of the multimeter, like so. And the multimeter is going to be sort of a bridge between the power supply and the motor. And then I'm going to connect the negative side of the multimeter to the positive side of the motor. It's going to be in between the circuit. So if we draw it on paper, so it's going to look like this. So we have the, I'm going to take a little piece of paper over here. So here we have the power supply with a plus and a minus. So the minus goes, and then there's the DC motor, DC, and down, so the negative one goes directly to the negative side of the DC motor, and then the positive side, it goes to the multimeter, and from the multimeter into the positive side of the DC motor. So basically the current flows through the multimeter, and then the multimeter is able to measure it, and then it can flow forward it to the DC motor. So that's the schematic approximately. So now the next thing is just to turn the power supply on, and along with that, so before we do that, also let's set it to the mode, set the multimeter to the mode where you can measure amperes, and here you can specify whether it's AC or DC voltage, and in our case it's DC voltage, so you make sure that you have the right setting over here. So I'm going to turn on the power supply, so you can hear that the motor starts spinning. So you can see that here we see 0.03 amps, and let's just see whether we can see the same value on the multimeter. And yes, so the multimeter shows that indeed the motor is consuming 0.029, or sometimes it jumps to 0.03. But yeah, so what we can conclude is that we actually can get a bit more precise measurement with the multimeter. So in my notes where I have DC motor, so I can add another entry. So with the power supply, we were measuring the power consumption as 0.03 amperes. So, but with the multimeter, we have 0.029. So next is the LEDs. So this LED strip. So let's measure that in a similar way. So let's make sure that so this is also drivable with 12 volts. So we know that in the power supply we have 12 volts as the setting already, and the limit of the current is 1.9 amps. It should be enough for this LED strip. So again, so I'm going to connect the negative test clip to the negative side of the negative wire connector of the LED strip. And let's do the same. Let's connect the positive clip of the power supply with the positive of the multimeter, and then the negative test clip of the multimeter to the positive test clip of the LEDs. Here we go. And yeah, with our notes here, so LED strip, power supply, multimeter. So we're gonna try to compare both of those. Okay, so I'm gonna switch on the multimeter. So set it to the DC voltage and so DC current and the ampere setting over here, and turn on the power supply. And you see that the whole scene got brighter, and we also see that power supply is showing 1.5 amps over here, and it's actually slowly going up. And if you look at the multimeter, then you see this 1.5 and 3, 8, 9, 5, 40. So this is an interesting thing. So when the LEDs are heating up, they are actually starting to draw more current. But yeah, you can see that there's a little offset from what There's a little difference between what the laboratory power supply shows and what a multimeter shows, but let's just make a snapshot. So at 1.54 it's showing 1.558, and you could also limit the voltage of the power supply, so which maybe we're gonna do, and see what how the measurements are different. Connect the test LEDs together, switch on the power supply, and fine-tune this to 1.5 amps, like so. Now reconnect as it was before through the multimeter. No. Like so, and now switching it on. So yeah, so now at 1.5 amps that we are giving with the power supply, we are getting 1.52 amps, 1.519 amps on the multimeter. So approximately the same. I'm actually wondering which one is more precise, the benchtop power supply or the multimeter. Okay, that's that. So this is how you can measure the current. So this is how you can measure the current for individual devices. But what if they are driven by a circuit? So let's explore that. So I have prepared 2 circuits over here. One is a DC motor driving circuit, and the other one is an LED board. So this is kind of an upgrade from like a version of the Hello board for these specific bright LEDs that Neil made, with a few additions. So it has a button that can toggle the LEDs on and off, and then it also has a connector where I can connect additional LEDs if needed. So let's start with the motherboard. So in order to make the motherboard work, we'll also need to connect a motor. So the way you attach the cables, it doesn't matter if you do not care in which direction the motor spins. What it matters if you need it to spin in a certain direction. So if you flip the cables, you also flip the direction of the motor. Okay, now the motor is connected. Now we need to connect the power supply. So I'm going to connect the red to the red. And then black to the black. So now it's connected, and we also know that the power supply is set to 12 volts. This is the voltage required to drive the board and also to drive the motor. But let's take a closer look at what this board consists of. So you see that there's the power port, so which is going to supply the board with 12 volts. Then it has a voltage regulator, which is going to downscale the voltage from 12 to 5 volts, so that the microcontroller, which is ATtiny412, can survive. And the reason why we are using the big voltage regulator here is because the ATtiny needs enough current in order to trigger the control pins, the control pins of the motor driver. So this is the motor driver chip, which is an H-bridge. And the way it works is, as you can see here, there are two lines going from the microcontroller to the motor driver, and these 2 lines are used to control the direction and the speed of the motor through the motor driver. And what the motor driver does, it connects the unregulated voltage, which is the 12 volts that is coming from this input here, to specific voltage and current that is being supplied to the motor through this connector over here. So the voltage regulator provides relatively clean separation between the between the voltage and the current needed in order to drive the logic or the microcontroller of the board, and the current and voltage needed in order to drive the motor. Additionally, here there is a trimmer, like a variable resistor that you can use in order to control the speed of the motor, and a button that you can use in order to change the direction. And so the default state is going to be just spinning, for the motor is spinning clockwise and at full speed now. So let's turn on the power supply now. And as you can see, it's turning clockwise, and while turning clockwise, it is consuming 0.04 volts. So what happens if I tune down the speed to 0? So now it stopped spinning. Let's see what happened to the amperes. So yeah, it dropped down to 0.01. And we can assume that the board alone, without driving the motor, is consuming 0.01 amperes. And then when the motor is spinning, it's consuming 0.04, which actually makes sense because as before, so we measured how much current does the DC motor consume at full speed. It was 0.03 amps. And if we subtract this from the amperes, so from the current measurement that we see here, so 0.04 minus 0.03 is actually 0.01. So this is the amount of current that the board consumes without us driving the motor. So you of course can use the multimeter, which you are encouraged to do, to get a more precise measurement, but this is roughly how you would do it. Okay, then also let's explore how the change of the direction works. And let's switch off the power supply and switch, change our attention to, change our focus to the LED board. Okay, so I'm not going to disconnect the motor, but I'm just going to disconnect this power supply over here. So this. So with the LEDs, it's different. So the board is designed in order to support 9 volts. So what I'm going to do before switching on the power supply, I'm going to disconnect one of the test LEDs and set the voltage on the power supply to 9 volts. Like this, switch it off for now, and then connect the test LED to the positive of the connector of the board. And yeah, before switching it on, let's discuss what's on this board. So there's, as you see, a connector, a power connector, and there's the ATtiny 412 chip. It has a power LED with a bypass capacitor and the current limiting resistor, and it has a button. So the button we're going to use in order to trigger the transistor over here. So also here, so from the main current supply, which is 9 volts, the current travels to a voltage regulator. So here we use the small one because we do not need a lot of current to drive the ATtiny, and the ATtiny doesn't need to do anything specific that needs more current than usual. So we reduce the voltage, we regulate the voltage to 5 volts with this voltage regulator over here. Then as we press the button, we are actually supplying a voltage to the pin which is connected to the gate of this transistor, so this MOSFET over here. And then the drain of the MOSFET is connected to this LED network, and then the source of the MOSFET is actually connected to the ground. I think so. Yeah, but the idea is that the drain and source of the transistor is connected together as soon as we supply voltage to the ground pin over here. So let's see how that looks in action. So I'm going to turn on the power supply over here. So as you see, the board alone is pulling 0.01 amperes, so which is pretty much the same as it's exactly the same that as the actually, like, in order to get exact measurement, you would need to connect the multimeter. But yeah, so as the other board, so it's the same amount of current. But now let's look at the board, and let's see what happens when we press the button. Whoop. Yeah, so these LEDs are quite bright, and you see also that the current measurement on the power supply changed from 0.01 to 0.545. So it's fluctuating, and it's probably rising because the LEDs are also, yeah, so they're heating up, and as they heat up, they are pulling more current. So then again, it will be kind of interesting to know what is the exact measurement of the multimeter, but that's up to you to do that. If you want to be, it starts to smoke. So you should limit the voltage to the amperes, the currents to, like, let's say 0.5 amps in this case. And that's it. So these LEDs are quite bright, but the thing is that they are heating up quite quickly, and the more they heat up, they eat more current, and then thus they heat up even more. So when you're designing a board and you really want it to last, then probably you should take extra consideration about, let's say, connecting the ground parts of these LEDs to a ground plane, and then attaching some sort of a heat sink to them. And preferably instead of FR1, you would probably use FR4, so you manufacture the board and the rest. But as for experimentation purposes, this is fine. It's just that in order to drive this, use the current limiting capabilities of the power supply. That's pretty much it. So just to summarize, we discussed how to use the laboratory power supply, how to use the multimeter to measure current in amperes. So we looked at two different power output devices. So one is the 12-volt DC motor, and the other one is this LED strip. And then we also looked at two different solutions that were designed to drive those two things digitally by using power components. So in this case, a transistor and an H-bridge. That's it for this. Like, additionally, so these are not the only output devices that you can choose to use for your final project or your project for this week. So we have other drivers, like stepper motor drivers, and it would be interesting for you also to learn how to use servo motors. For all of those things, just ask us and take a look at the Fab Academy class page. And yeah, I hope to see you measuring things with the laboratory power supply and not getting shocked. Thank you.